Writing code for quantum computers always involves some layers of abstraction. Learn about a new language that makes it easier to create working circuits and an enterprise-level development tool you can use for free in this episode of the Post-Quantum World. I'm your host, Konstantinos Karagiannis. I lead quantum computing services at Protiviti, where we're helping companies prepare for the benefits and threats of this exploding field. I hope you'll join each episode as we explore the technology and business impacts of this post-quantum era. Our guest today is the co-founder and head of algorithms at Classiq, Amir Naveh. Welcome to the show.
Hi, thank you. Thank you for having me.
Yeah, and we've had Classiq on. It was over 2 years ago, so it's about time that you guys come back, and we'll get to why in a little bit. But can you tell us a little bit about how you found your way to quantum?
Yeah, for sure. So, I was into physics from in high school. I was in the physics Olympics. That was a long time ago, and then I was in the Israeli Defense Forces, doing everything from algorithms to physics to satellite engineering and just all over the place. And then I remember a bit of quantum physics from the time I actually learned about physics formally. And then we were thinking about forming a company, and we were actually going to quite a lot of places, AI and computer vision and brain-computer interfaces, and a lot of different ideas that me and Nir, my co-founder, had. And then Yehuda, who is also my father, was working at IBM, leading one of the quantum software teams at IBM. And at some point, we started talking with him about quantum software, and it just felt like the right thing to do, where you can build a really big company in a technology that's not quite there yet, but is going to be there in a few years, which is exactly the right place to build a big company. So from there, we never looked back.
Yeah, and in case and I know plenty of our listeners weren't here 60 some episodes ago when we had Classiq on. If you want to give a little refresh or introduction for many on what Classiq is and what your general approach is.
Sure. Yeah, of course. So Classiq was built under the understanding that quantum computers are going to be here, and they're going to be here in a few years. And to build the software for using these computers follows a lot of the challenges that we've had decades ago in creating classical software. I mean, you're not writing at the gate level or at the punch card level anymore. You have operating systems and compilers which enable you to express your ideas more or less in a human readable way. And at the output, you have the gates that are actually working on the classical computers, on the chips. But in quantum, well, there's also quantum logic. You also have quantum gates and quantum machines, right? But you need to have this abstraction in order, first, that you can describe what you want, what is the algorithm or what is the program you want to run. But also in these compilation steps, we sometimes forget how many optimization steps are happening from the human level down to the machine level. And if we don't create these abstractions, then we have to do things manually, and people are very bad at optimizing large programs. So without this technology stack, in some sense, you're very limited on what you can do with a quantum computer. And this is the technology that Classiq is creating, enabling this abstraction and automation, kind of like the analog to compilers and operating systems in the classical world.
Yeah, there's plenty there that we're going to stick pins in and dive in on. So thanks for that overview. If I think of the platform, it's actually, I've seen a diagram drawn pretty nicely of how the platform works. You can have a IDE, you can have a Python SDK, and then you can drill down into all the other layers like a synthesis engine, et cetera. So I don't know if you wanted to kind of like describe what a person sees in those different ways when they're trying to interact with the platform.
Yeah, of course. That's a great question. So the first thing we need to understand is that the person needs to describe their algorithm, and this we call the model of the quantum algorithm. Now they can describe it using a graphical interface. They can describe it using Python. They can describe it using our modeling language. But in essence, it's always describing the logic of the quantum program. So defining which functions or which building blocks you're using and how they connect or how the inputs and outputs work between each of them in order to create a full logical program. This is something that the human does because they understand what they're trying to achieve. And then this is the input for us. This goes into a compiler or a synthesis engine, which takes this model, which is abstract, and creates a concrete implementation of the actual gate level, machine level code that can actually run on a quantum computer. So if people are aware, for example, of Qiskit, you have formats called QASM quantum assembly. So that would be the output of the compiler or the synthesis engine, which describes the concrete program. Now, from one model, you can have a very large number of concrete programs, depending if you want to optimize on the number of qubits, on the depth, on the errors. If you know the specific hardware, then it will be wired differently. So even a single function can have many different implementations, and the full algorithm can have a very, very large space of different solutions. So this is the first step. And then once you have this concrete quantum program, sometimes also with some classical instructions on how to iterate this quantum program many times. Then you send it over to a simulator or to an actual quantum hardware, which is also not always trivial to do because you have many different interfaces and every single machine works a bit differently. So this is kind of an end-to-end platform where you always begin with describing the quantum program using a model. Then it's compiled into a concrete implementation, which is then run on hardware or simulator. You get the results. This is basically the flow.
Great. Yeah. And so for those listening, um, you choose how you want to start the process. Like, do you want to be really, really abstract? Like, I mean, to hopelessly simplify it here, basically moving around little colored blocks to create a circle, or do you want to actually drill down on the code level, right? And then you end up with this model, and then that gets passed on to the rest of the platform to do the synthesis, to create output code, and then actually send it to execute on some kind of target.
Exactly.
Yeah.
And at the maybe um, easiest level, we have quite a large library of pre-built applications and algorithms. You can just open one of them, change whatever parameters you want. Shor's algorithm, just put in the number you want to factorize and then run it, and you'll get an answer. So that's the simplest way. But if you want to change within Shor's algorithm how the modular exponentiation is being implemented, you can go into that level. I mean, you can work at many different layers of this abstraction layer. And of course, the more you go inside, the more control you have over what is going to happen at the end.
Yeah, and a little bit, I want to talk about those Classiq models that you have, so the pre-built stuff that people can start playing with. I definitely want to get to that. So now I'm sort of visualizing this and moving through the layers so everyone could understand like the workflow. The newest thing here is QMOD. So QMOD, that's a new language with constructs for quantum. Did you want to talk a little bit about that and how it might be an easier way for folks to get started than more of the like classic Python SDK?
Yes, this is really important. So I wish we wouldn't have had to build a language. I wish there were something that was descriptive enough so that we could use it off the shelf. For classical computing, we have many of these languages, from languages for chip design like Verilog to languages that for algorithm development like Python. But in quantum, let me give you an example. If you have a multi-control X gate, which is a very, very common construct in many quantum algorithms, then in any other quantum programming language, you have to specify the implementation. You have to say how many auxiliary qubits it's using, and then how these auxiliary qubits are wired to other auxiliary qubits. It's forcing you to manage the memory and manage the different implementations. And this is hard coded in the language. It's not something you can bypass. So we had to give the users some way in which they can describe the quantum algorithm without specifying the implementation, so that first it's easier for them, and second that you can do many different levels of optimization on this algorithm that the user doesn't really care about. The user doesn't care about wiring the auxiliaries in an optimal way. They just want to get a circuit with minimal number of qubits or that fits within some specific hardware. So this QMOD, which is just the suffix for quantum model, right? This is every quantum model you create with Classiq will end with QMOD, which is just your way of saying, I've just described a quantum algorithm or a quantum program. And it's really, I mean, it's always kind of frustrating to learn a new language, but here everyone who uses this tells us, wow, this is so much easier. I mean, yeah, I could work with the gates directly and wire the qubits, but here you're giving me a language that enables me to describe what I care about. The CXs are just the implementations. I care about the logic. This is a language that's enabling me to describe the logic, and this is kind of the major step here.
So QMOD comes in earlier in the steps, and you build your model with this language. Then you send it off. Then you still, in theory, end up with code that gets output in the end if you did want to go in and tweak, right? Like if you wanted to tweak QASM or something later on.
Yeah, of course. I mean, there are different levels also of the abstraction at the modeling level, but of course, after you press synthesize, like there's a synthesize button in the IDE, for example, you press it, and then you can download the quantum assembly. And there, sure, I mean, you can take this and change the C0 gate into a CZ gate and change one function into another function, and it'll work. It's a well-defined syntax, but it's at a much at a level much closer to the actual hardware.
Yeah, I just want to make sure listeners understand that just because it's a language you created and it works in your world, so to speak, it doesn't limit you after that. It does actually output an interface with the rest of the ecosystem.
For sure. We always say that, I mean, you can take a QMOD and output QASM from this. And you can also, if you want, you can take a QASM and you can just upload it and you will see it in our platform. I mean, we're very much supportive of the lower levels of the stack. That's very helpful. I mean, the fact that there's somewhat of a standard in many people accepting QASM 3 or Q#, which we also support, this is important. We don't want to replace those levels.
So while you're experimenting with QMOD, you don't really have to worry about what your target will ultimately be. Will you be sending it to IBM? Will you be sending it to Bracket? It doesn't matter, right? Like you can just play like more freely.
Yeah, for sure. And also I encourage listeners, of course, to enter our platform. It's really easy. Just go to platform.classiq.io. And then you can see in the place where you write the QMOD, you can also specify the hardware. Now, you don't have to. And then you'll get some circuit that's, ready to run. But if you know the hardware in advance, it'll make decisions based on the hardware. That's really strong. If you have full connectivity, you'll get a different circuit than if you have nearest neighbor connectivity in the qubits. Mm-hmm. It implies different implementations, which will be more optimal for your specific hardware. So this is really nice how kind of knowing what the target will be helps the optimization process. You don't have to do it, but it can help.
Can you, so you can get the optimization by knowing while you're in QMOD. If later on you decide on a different platform, is it possible to apply any kind of optimization then?
Yeah, the QMOD stays the same. This is kind of adding additional constraints. So I have a model. Let's say my model is saying, do this Grover search problem. Now I can say, so this will stay the same. But now I'm putting one time, I'm saying, look, the constraint is you have up to 100 qubits to work with. So I'll get one circuit. And on the second time, I'll say, look, use as many 2-qubit gates, as few 2-qubit gates as possible. So I may get a circuit with more than 100 qubits, but I'll get less 2-qubit gates. But they're all stemming from the same QMOD, from the same model. I didn't change the QMOD, I just put different constraints and preferences. So this is what the hardware is also doing. If I put a different hardware, it's always the same model, but I'm just changing how the constraints and preferences are, how the synthesis engine treats them.
Yeah,
That makes sense.
and when I was looking at how it works, and of course sometimes I ask questions I know the answer to already, but when I was looking at how this works, I just want to make sure listeners understood that this is something that might, even though it seems abstract and kind of like high level, it might lead to a greater understanding of what goes on way, way low level. So that's what impressed me when I looked
Yeah,
at it.
for sure. I mean, I'd really encourage, we have examples. For example, Grover search is a good example because it's a simple algorithm. When you're looking at the model, it's really straightforward. Do Hadamard, then do the oracle, and then if your oracle, for example, is an arithmetic function, you write the arithmetic function, and then you have the logic, and then do the diffuser. And this is so simple. This is just how Grover works. And then repeat this so many times. That's really easy. But in each of these steps, right, in the arithmetic within the oracle, or in the MCX gate within the diffuser, there is so much to do. And this is, you don't care. You just want, when you're doing the diffuser, you just want to flip the state vector there. You don't really care how many auxiliaries the diffuser is going to use. And you don't really care how the uncomputation was managed within the arithmetic within the oracle. So this is, it makes it much easier to read. If I would have drilled this down to the CNOT level, you wouldn't understand what's going on. So this is, it's a benefit both for the optimization, but also for readability. This is kind of the most direct way how you can describe Grover's algorithm formally.
And the output here is intended to be enterprise grade ultimately. Like the hope is to build a use case that can actually be applied for some business purpose one day. But what's interesting is you can actually do this for free, which I thought was interesting now. So you want to talk a little bit about the new licensing model, about free for personal, and then how it switches over?
Yeah, that's a really good point. Actually, I was in the quantum information processing conference just last week in Taiwan, and what I found, it was really painful for me that a lot of people didn't know this. So this is a good platform maybe to kind of shout out to the world. The platform is open. You can use it for anything that's non-commercial. So if you're a researcher, if you're just an individual, you want to try it out, to test it, signing up takes maybe 10 seconds. And there you are. You can work with the IDE. You can do pip install Classiq and work with the SDK. No one's going to limit you. We're not charging anything. We just want to create a large community around this. So this is really important for us. Of course, if you're working at an enterprise team, then we'd be happy to discuss and work together on creating what's interesting. But for non-commercial community use, this is open for everyone, and it's our biggest passion to work with as many people as possible.
Yeah, so it lowers the barrier entry too. If you want to maybe consider using it at your company or your team, whatever, and I'm speaking to listeners right now, they can go try it out. And of course, all the links are in the show notes for all this. It does take like 10 seconds to sign up and get started. It's really quick and easy. And you can just use the interface right in your browser, basically, to get started. And we've talked a few times now about this like sample code and these sample use cases that appear. So they're called Classiq models. And I urge listeners to go take a look at them. There's a lot there. There's chemistry, cybersecurity, there's finance, logistics, optimization, basically all the stuff you would expect to see. But when you click in on them, there's actually papers behind some of the models. And they're sort of the basis of them. And I thought it was funny because I was looking at the patching management one under cybersecurity. And it's based on, I was like, does this remind me of something? I look in, sure enough, it was based on the paper by Mark Carney, who was on this show from Quantum Village at DEF CON, the kill chain paper that he wrote. So I have some deep experience with that paper, so I thought it was interesting that to see it just like implemented in this way. Um, did you want to talk about some other sample use cases that are interesting to you from the models?
So first, yeah, I mean, just kind of maybe restating what you said. I'm really excited about this. It's a project that the team I'm working with is kind of working on this for a long time. We said, okay, we've built this technology, we've built this platform where you can do anything. Let's do the things, and we've been working with a lot of customers and users, and we have quite a lot of experience on what's interesting. And we said, okay, we won't like do everything, but at least a few use cases in every industry, and just show how easy it is, or how approachable this is. This was really important for us. And actually, specifically in cybersecurity, this is something. I mean, uh, being an Israeli company comes with usually a lot of the people in your company are ex IDF cyber experts. So we have maybe a large percentage of the company come from a cyber background. So all of them kind of know the cyber use cases by heart. So we said, yeah, maybe it's good to show some cyber applications that are not only Shore's algorithm or offensive, but also defensive cyber. Like, how can you use quantum to protect your systems and your vulnerabilities? So this is exciting. I think maybe the one thing I would emphasize, actually, the patch management is part of that, is doing optimization problems with Classiq is really quite nice. It's even a step further from what I described earlier on doing, for example, Grover's algorithm, where you can work with the building block level. Because if you have an optimization problem that's well defined, meaning you have your variables, your constraints, and your domains for the variables, and you have some optimization function, you can write all of these down in a very straightforward way. We have an interface for defining these optimization problems. And then you can get a quantum algorithm. You don't even need to understand the underlying Grover or QAOA scheme or whatever. You can, of course, you can always dive into it, but if you're a non-quantum expert, for example, and you just want to see how you have this optimization problem in mind, you want to see how this vertex cover or graph coloring or whatever other problem maps into a quantum computer, all you need to do is define the problem. So this is another step forward where, I mean, it's not always the case for every single problem, but in optimization, we've done this extra step because a lot of problems are optimization problems.
Yeah, if you go and click inside of the optimization, and again, the links are in the show notes, you'll be surprised by how many there are there. There's like a weirdly specific electric grid optimization, and then it gets more general, like max cut, stuff like that. So I was like, whoa, I was expecting to see two things in there. I didn't expect to see that many. So yeah, it's a pretty nice starting point, and you can potentially build something worthwhile. But remember, if you build it for commercial purposes, eventually then the licensing kicks in. But for now, you can start playing. Absolutely. And is there anything you're doing to sort of like entice more of this community for education, like for building more of these samples?
Yeah, that's part of the reason why we put this publicly on GitHub. Well, it doesn't look as pretty as I would have wanted, but being a startup, sometimes you just put it out there and then you iterate on it being nicer. But we really encourage people to work with what we have, and then to kind of build their own. There's also a Slack community that's moderated by Classiq. There's a link also in the platform, really easy to connect. And we have maybe 5,000 people there right now. And it's very active. And in the company, it's very important for us to answer everything. So you won't have an unanswered question in this community. So anything I don't know, you're new to quantum, or you have this very specific paper that you're trying to implement and you got stuck with some, I don't know, some syntax error or whatever, just ping us over there. And yeah, I mean, also you can reach out to anyone from the company, to schedule a workshop or a training or whatever. We're very, very happy to engage with anyone that's interested. It's a small community, so everyone is welcome, and we'd be happy to put in the efforts.
Are you seeing users answering each other's questions? Like, oh, I had
Yes.
that problem and I did this, that kind of typical forum stuff?
Yeah, that was really nice. We did kind of a course with Classiq in the past few months, like 10 teams, each doing a research project with the platform. And then, like, people from one group were answering the people from another group. That was really nice. Yeah, for sure. I mean, I won't say it's fully autonomous, like everything is working and we're just sitting back and looking at how it's working. But yeah, for sure, the community is very active, and yeah, the usage, when we're looking at the usage graphs, it's growing on a daily basis, and that's the main goal, just to see how the numbers are growing and how the community is adapting. That's really nice.
So we've seen that some papers are the basis for what becomes a classic model. Have any, to your knowledge, have any of those folks in that community used one of the classic models to then build and publish a paper? Has it gone the other way?
So, in what I mentioned just now, so there are quite a few projects. I don't know if they're going to, I think some of them are going to publish on Archive, but I don't know
Hmm.
if they're going to try and do in peer reviewed journals as well. I know quite a lot of research groups are working on implementing circuits with the platform. I hope they gain advantage from it and use it properly. For us, yeah, the research community is very important right now. I mean, that's what leads the ecosystem. So I know there are quite a few, and of course, when working with enterprise customers, that's quite an often thing they do. So either uh, by themselves and with our support, or together with us, they sometimes want to create research papers that there are at least a few that are currently in progress and will probably be public in the coming months.
That's great. And before we start to wind down, are there any other features that you're currently trying to implement that maybe you can give us a little sneak peek about?
Yeah, it's a podcast. So actually, this is something that's sometimes much nicer shown than said, but I'll try with in a few words. Um, One of the ways to describe a quantum program is graphically. So you can, if you have the building blocks, you can wire them together, and this is quite strong because you're just saying how the inputs and outputs behave. And for example, you're not saying how the memory behaves. You're just defining the logic. So we call this, I mean, this is our graphical interface. The output of this is the same QMOD. It's the same structure of language. You can also work with this textually, but actually seeing this graphical way of viewing and working with quantum circuits, it makes kind of, there's an aha moment for many people. Like they understand why this is fundamentally different than working with gate level programming languages like Qiskit. And this is, I think, really important. I mean, sometimes it's just easier working graphically, but also just for understanding, the different layers of how this abstraction works. This is really important. So this is something, I mean, at the beta level, we already have it. Some of our early access people are using this already, and I hope we'll have it open for wide usage in the next 1 or 2 months.
So it's sort of like a sense of how much can you represent with a rectangle on the screen, right? It's like you have this high level rectangle, and inside there's a bunch of little ones representing actual gates, and so on and so forth. And people
Exactly.
getting familiar with this idea.
Yeah, I mean, for anyone, not that I'm a LabVIEW fan, I'm not, I hate LabVIEW, but for anyone that's worked with LabVIEW or with Simulink by MATLAB, this is kind of the same ideas of design, right? You describe the logic, and then code is generated.
Hmm.
So I mean, you can work with the Python SDK and you can work with the textual language. I'm not forcing anyone to work at the graphical level, but it gives some insight and it's quite exciting. And I'm saying this as a person that really doesn't like usually graphical tools too much. I'm
Yeah,
not a
well, yeah,
super guy.
seeing you do definitely have to see it. So I urge people, since it is free and it is powerful, you can just go take a look at the links in the show notes and give this a try for yourself. So yeah, Amir, thank you so much for coming on. I really appreciate it, and I hope you get a lot more people added to those ranks inside of that channel.
Yeah, thanks. That was it was really nice talking, and I mean, I feel your love for the platform as well. So this is, I mean, it's really nice talking, and I hope we'll be able to come in 2 more years and share even more exciting
Yeah.
advances and innovations. So yeah, thank you so much for having me.
Now it's time for Coherence, the Quantum Executive Summary, where I take a moment to highlight some of the business impacts we discussed today in case things got too nerdy at times. Let's recap. Classiq makes quantum coding easy with a development platform that enables multiple levels of abstraction and fine-tuning. It's all about translating algorithms to working code, and Classiq calls this description of a quantum algorithm a model. To describe or define a model, you can dig into a Python SDK, sure, but you can also program in a more modular way, literally moving around code blocks to build circuits. A new language called QMOD makes it easy to describe the logic of a model for the platform to then run in its synthesis engine. We've talked about quantum computing being a full stack here before, and this tool makes it easy to work at your own desired level. If you're struggling to get started, you can modify numerous provided use case examples with your own parameters. For example, add the number you want to factor to Shor's algorithm code. After an algorithm is synthesized, it can be output to OpenChasm. This allows for interoperability and the ability to code without worrying about the backend target. One of the biggest developments in the platform is that you can now use the full tool for free for personal use. Check out the links in the show notes to get started on enterprise-level coding today. A license will be required for commercial use. That does it for this episode. Thanks to Amir Naveh for joining to discuss Classiq. And thank you for listening. If you enjoyed the show, please subscribe to Protiviti's The Post-Quantum World, and maybe leave a review to help others find us. Be sure to follow me on all socials at Constant Hacker. That's Constant with a K, Hacker. You'll find links there to what we're doing in quantum computing services at Protiviti. You can also DM me questions or suggestions for what you'd like to hear on the show. I'll be gathering those for an AMA episode I'd like to do soon. For more information on our quantum services, check out Protiviti.com or follow Protiviti Tech on Twitter and LinkedIn. Until next time, be kind and stay quantum curious.